A cladded fiber optic cable. A fiber optic cable consists of a thin cylindrical core with thickness d made of a material with index of refraction n sub 2 less than n sub 1. So this is the fiber optic cable, index of refraction n sub 1 greater than n sub 2, the encapsulating material. Light rays traveling within the core remain trapped in the core provided they do not strike the core cladding interface at an angle larger than the critical angle for total internal reflection. Part A. Figure shows a light ray traveling within a cable bent to its critical extent, beyond which light will leak out of the core. The radius of curvature of the center of the core is capital R. Derive an expression for the angle of incidence theta, that's with respect to the normal here, at which the indicated light ray strikes the outer edge of the core. Part B, determine the critical radius r in terms of n1, n2, and d, the thickness of the fiber optic cable. Part C, a typical fiber optic cable has a 50 micrometer thick core with index of refraction 1.4475 and has a cladding with index of refraction 1.4440. What is the minimum radius of curvature for this cable? Now, you can see that we have this light ray incident on the normal at an angle theta here, and here we have a distance AC, which is capital R plus d over 2. So that's basically so this is our capital R, so this is our capital R plus d over 2. So, and we have a distance BC that is capital R minus d over 2. So this was capital R minus d over 2. And this angle theta is basically due to law of reflection will be the same angle theta here when we have total internal reflection. So from in part A, if we write the total internal reflection, sine of theta is going to be equal to, you can see here, because we have a 90-degree angle on this side, capital R minus d over 2 divided by capital R plus d over 2. So this is going to be capital R minus d over 2 divided by capital R plus d over 2. This basically we see from the ABC triangle. So theta, the angle of incidence, will be sine inverse of capital R minus d over 2 divided by capital R plus d over 2. Okay, so we can see that we have this ray being tangent to the inner cladding at point B, so that's why we have this angle 90 degrees. So we can find the sine of the angle theta from this ABC triangle. Now in part B, we want to determine the critical radius r in terms of n1, n2, and d. So if I write the condition for total internal reflection, n1 sine theta must be equal to n2 sine 90 for the critical radius. So we will find that sine theta is basically equal to r minus capital R minus d over 2 divided by capital R plus d over 2, which is the ratio n2 divided by n1. So for this critical angle theta here, if we just have the onset of onset of total internal reflection, we will have a 90-degree angle here. So we will have basically n1 sine theta equals n2 sine 90. So this will give us 2r minus d divided by 2r plus d equals n2 divided by n1. And theta is now the critical angle. Okay, so we will find that 2n1 r, capital R, minus dn1 is equal to 2n2 r plus dn2. So when we have the inners and outers multiplied, in 2r parentheses, I have n1 minus n2 is equal to, in d parentheses, I have n1 plus n2 on the right hand side. So this gives me the critical radius of curvature, capital R, to be d over 2 n1 plus n2 divided by n1 minus n2. In part C, we have a numerical example. The thickness is 50 micrometers, so D is 50 micrometers. So I will have capital R equals 50 10 to minus 6 meters divided by 2, and 1 plus n2, we will have a 1.4440 plus 1.4475 divided by n1 minus n2, 1.4475 minus 1.4440, and this gives us a radius of curvature 20.7 millimeters. All right. So we have a cladded fiber optic cable. The cable has a thickness D. It has a material with index of refraction N2 less than N1. So that's the cladding material. N2 is less than N1. Light rays traveling within the core remain trapped in the core, provided they do not strike the core cladding interface at an angle larger than the critical angle. So when they hit the interface between the cladding and the material here, if we have total internal reflection, we will have this angle theta equal to this angle theta. So if the cable is bent to its critical extent beyond which light will leak out, the radius of curvature of the center of the core is r. We want to know an expression for angle of incidence theta, and that is basically found by looking at this triangle, ABC triangle here. This is a right triangle. We have sine of theta equals r minus d over 2 over r plus, capital R plus d over 2. We want to determine the critical radius r in terms of n1, n2, and d. Writing Snell's law at this interface, we have n1 sine theta equals n2 sine 90 for the critical angle of total internal reflection, and that sine theta is r minus d over 2 over r plus d over 2. So we will have this is equal to n2 over n1, giving us r of d over 2 and 1 plus n2 over n1 minus n2. If we substitute for d 50 micrometers and for n1 and n2 1.440 and 1.4475, we find the critical radius of curvature 20.7 millimeters.